We want to know if there are manifolds such that every vector bundle over such a manifold is always trivial. And indeed, we will introduce today some results that are going to help to identify manifolds that have such a property. We want to know if there are spaces and manifolds such that every vector bundle over M is trivial. For instance, is this true for Rn, for Sn? We don't know. So in order to solve this problem, or at least to find spaces that satisfy this property, we are going to introduce today some interesting results about triviality of vector bundles. The first interesting result that we are going to see in this lecture is the following theorem. Consider, vector bundle C whose base is M times the closed interval 0, 1, the total space is E, and the projection is P. Let us suppose that it is a CR vector bundle where R is between 1 and infinity. Then each point X in M has an open neighborhood U that is contained in M such that the restriction of the C to U times I is indeed trivial. Okay? Why is this true? What we have is that given xt, any point in the product of M and I, there exists an open neighborhood W of xt in M times I such that the restriction of C to W is trivial. This is just a consequence of the definition of vector bundle. Given any point in the base, there is a neighborhood such that the restriction of the vector bundle to such neighborhood is trivial. Okay? As a consequence of this, okay, we fix a point x0 and M, and we are going to have triviality in the neighborhood of every point of the form x0 t. So because of that, there exists a partition of the closed interval 0, 1, okay, such that, well, and open neighborhoods uj of the point x0 in M and bg of the closed interval tj plus 1 in I such that the restriction of psi to uj times bj is trivial. Okay, this is just a consequence of the compactness of the closed interval 0, 1. Right? Indeed, we can suppose that all these uj's are the same. Okay, because we can just define u being the intersection of all the uj's. And in this case, we just have that the restriction of C to U times BG is trivial. So we have triviality in the restriction of C to U times okay, T0, T1, the restriction of C to U times T1, T2, and so on. Finally, the restriction of C to the product of U and the closed interval whose extremes are Tn minus 1 and Tn. Okay, in all these, indeed, all these vector bundles are trivial. And what we want is, if we have, for instance, triviality in the neighborhood of these two sets, we want to obtain that the restriction of C to the union is still trivial. In that way, we can replace two of them with one, in which we still have triviality, and step by step, we end up proving that the restriction of C to U times the closed interval is indeed trivial. Okay, so let's do this. Very good. What we have is that, for instance, let's focus on the first here on these two sets. Let's call it T0 equals 0. T2, let's call it 1 because it doesn't matter. If it's not 1, the proof is going to be completely analogous. And T1 equals C. And we know that for the first fiber bundle here, there exists a vector bundle chart. Okay, here we have 0, 1, C, and here we are going to consider A and B. Let us explain what is A and B. So we're going to have a vector bundle chart, okay, over U times 0B. Okay. This is just a vector bundle chart. Okay, and what happens is that Bj is indeed a neighborhood of 0C. So we can obtain here a vector bundle chart because the restriction is trivial, that is defined not just over U times this interval, but over U times a slightly bigger interval. Okay, this is the interval 0C. We can define it in an interval of the form 0B with B slightly greater than C. Okay, in the same way, we are going to have a second vector bundle chart because this second vector bundle is also trivial. And we have that this second vector bundle chart is going to be defined over U times the closed interval A1. Again, here we have that this is C1, but for the same reason that in the previous case, we can actually obtain this vector bundle chart for a slightly bigger interval. Okay, so here we have phi 2 U times A1 times Rn, and here the projection. Okay, so we have these two vector bundle charts. And now we are going to consider the transition function defined in U times the interval AB with values in the linear group. such that it associates at every point xt the composition of the inverse of phi sub 2 xt with phi sub 1 xt. Okay? If for instance, if our vector bundle is CR, this map is CR, right? Now, we are going to consider H a C infinity map from A1 to AB, such that the image of T is equal to T for all T in AC, right? Here we have 0, 1, C, A, and B. Okay, this is possible, it's not really very difficult. And what we want now is actually defining a new vector bundle chart for actually u times the interval 0, 1, right? So we need here to define a new vector bundle chart, which is going to show actually that the restriction is trivial, okay, over u times 0, 1, and with values in u times the closed interval times Rn, right? And so we have to define phi of xt. We are going to define it as phi sub 1 of xt if x belongs to u and t belongs to the closed interval 0c. Very good. And we are going to define it as g of x of ht composed with phi sub 2 xt if x belongs to u, of course, and t belongs to the closed interval a1. So that's going to be our definition. Okay, first of all, there is no problem defining this for points such that t belongs to 0c, because this is defined when x belongs to u and t belongs to the interval 0b. So 0c is contained in 0b, no problem. And here, this expression is defined when t belongs to the closed interval a1, so no problem. And the same thing happens here, because when t belongs to a1, ht belongs to ab, and g is defined when the first component belongs to u and the second belongs to ab. So everything is well defined. Moreover, if we are dealing with CR vector bundles, everything in here is CR. Yeah, this is obviously CR, this is obviously CR, and here the transition functions are CR and H is infinity, so everything is CR. That's not going to be an issue. So the unique thing that remains to be proved is that obviously the definition is a good one, that when t belongs to the intersection of these two intervals, the definition of these maps is the same, right? So let's see if that is true. Okay, so we have this when t belongs to 0c, and then g of h x ht composed with phi sub 2 xt if t belongs to a1. Okay, let's see what happens when with the second expression when T belongs to the intersection of these two intervals. So to the interval AC, closed interval AC. In that case, what happens is that h of t is equal to t. That's a property that holds true for this interval. So the second expression is going to be g of xt, the composition of phi sub 2 of xt with g of xt. But g of xt is just the composition of the inverse of phi sub 2 xt with phi sub 1 xt. So we get that the final value is phi sub 1 xt, and so the two definitions coincide. And so in this way, we prove that if we have a fiber bundle, a vector bundle over a manifold times a closed interval, there is always a neighborhood of every of the points in M, okay, a neighborhood U, such that the restriction to U times I is trivial. So, in other words, in the direction defined by the closed interval, our vector bundle is trivial. As a corollary of the previous theorem, we have that every CR vector bundle with R between 1 and infinity over an interval is trivial, because we just have to apply the result to the product of a point, or of zero if you want, and a closed interval. Okay, so we have our first result of triviality. Every vector bundle over an interval is always trivial. The following result is an homotopy extension theorem, and it is very useful to identify isomorphic vector bundles. So let us consider M and N differentiable manifolds, for instance, C infinity manifolds, and let us consider C a closed subset of our manifold M. And two open sets, B and U, such that C, the closed set, is contained in B, B is contained in the closure of B, that is contained in U. We are going to fix R between 0 and infinity, and suppose that this diagram over here is commutative. F is a CR map from M to M, but obviously we can consider F also as a CR map from M times 0 to M, okay? And what happens is that if we consider here M and here the interval, the closed interval, and here we have U, this set over here is indeed U times I, and it is where G is defined. F is just defined in M, or if we prefer, M times 0. So where are these two maps defined simultaneously? In this set over here, which is U times 0. And what we are requiring is that both maps are defined, they are equal in such a set, okay? That's exactly the same thing as requiring that this diagram is commutative, okay? So what we want to prove is that there exists H, okay, which is a CR map defined in M times the closed interval with values in M, such that the restriction of H to M times 0 is equal to F, and the restriction to V times I is equal to G. Okay? So in other words, we want that H is equal to F here, and in a slightly smaller open set V, we want that H is equal to G. Let's see how we can actually show this. So let's recall that C is a closed set which is containing B, which is containing the closure of B, which is containing U, right? And we consider lambda be a, for instance, a C infinity function, okay, defined in M and with values in 0, 1, such that lambda is equal to 1 in B, and the support of lambda is contained in U. This is possible because we can actually make the support of lambda to be slightly bigger than the closure of B, and since this closure is contained in U, we can actually achieve that the support of lambda is contained in U. And now we are going to define H. Let us recall that H is a CR map defined in M times the closed interval and with values in M. And okay, we have to define H of xt, and we say that it is going to be g of x lambda xt if x belongs to U, and h of xt is going to be the image of x by f if x does not belong to the support of lambda. Okay? Again, we don't have any issue with whether these maps are CR, because f is CR, g is CR, and lambda is even C infinity. So if the definition is correct, it's going to be CR. And when we consider the union of U and the complement of the support of lambda, since the support of lambda is contained in U, this union is the whole M. So we are defining H for every point in M times the closed interval, right? Moreover, what we have is that H of x0 is equal always to f of x, right? Because if x does not belong to the support, it's already f of x. And if x belongs to U, what happens is that this lambda times 0 is 0, and g of x0 is equal to f of x. So we have that property. And moreover, if xt belongs to B times I, what we get is that h of xt is equal to what? X belongs to B, so x belongs to U, so we can apply the first definition, and it's going to be g of x lambda x, but lambda x is equal to 1 for the points in B, so it's g of xt, and that's what we wanted to prove, okay? So the unique thing that remains to be proved is that the definition is correct. In other words, that when we have a point that belongs to U and it's not in the support of lambda, then these two definitions are the same, okay? So we are going to write down the definition again. Okay, if x does not belong to the support of lambda. What happens if x belongs to U, but it doesn't belong to the support of lambda? Right, let us consider the second definition. G of x lambda xt, if x does not belong to the support of lambda, lambda fixes 0. So this is g of x0, which is equal to f of x. which is actually the second definition. So indeed, H is well defined, and we get our homotopy, right? And this completes the proof. The following result is a consequence of the homotopy extension theorem. Let M and N be differentiable manifolds. For instance, we can suppose that they are C-infinity manifolds, and consider a closed subset C of M. Now, let F be a continuous map from M to N, and G a homotopy of the restriction to C. That means that G of x0 is equal to f of x if x belongs to C, right? Now assume that this small g stands to a map capital G, which is defined in U times I. U is an open set that is a neighborhood of C, such that capital G is a homotopy of the restriction of F to U. So what we are requiring here is that capital G of x0 is equal to f of x if x belongs to U. Under this hypothesis, then small g stands to a homotopy calligraphic G, okay, defined in M times I of F. So what we are going to get is that calligraphic G of x0 is equal to f of x if x belongs to M, right? So this result is a pretty straightforward consequence of the previous theorem. Let us remark that if we consider here that F is CR, small g is CR, and capital G is also CR, then calligraphic G can be supposed to be CR, because that's what happens with the previous theorem. It holds true for every class of differentiability. Right. A consequence of the homotopy extension theorem is this theorem over here. If we have C a CR vector bundle over M times I, M times the closed interval, and R is between 0 and infinity, then C is CR isomorphic to the restriction of C to, here it should be M times 0 times I. So the first thing that we should consider is, what does it mean C times I, right? So when we have a vector bundle, one way of giving a vector bundle is actually giving an atlas of vector bundle charts. But we can also give a vector bundle by considering the transition functions. Okay? Now, we could actually give a vector bundle over M times I by using these transition functions. Indeed, we are going to consider the following open cover of M times the closed interval, right? And we are going to define the transition functions in the intersection of any pair of sets of this form. Here we have that this is the intersection of ui and ug times the closed interval I. And what we do is sending a point xt just in g sub ij of x. So essentially, the definition is not going to depend on t. And the vector bundle obtained in this way is trivial in the direction of the closed interval. How do we prove this theorem? I'm not going to give here the details, but the idea is this result is actually true locally. We already saw that. We already saw that this result is true if we restrict ourselves to a small neighborhood of a point. And so what we have to do is pasting these local results. We can actually consider a cover by compact sets, by a small compact sets, a locally finite cover, such that the result is true in the neighborhood of these compact sets, and try to show that if it's true for one compact set and then other, then it's true for the union. And in that step, we have to use the homotopy extension theorem, okay? I'm not going to provide the details of this result here now. A consequence of the previous theorem is that if we have C1 and C2 CR vector bundles over a differentiable manifold M, then they are CR isomorphic if and only if there exists a CR vector bundle eta over M times I, such that psi I is isomorphic to the restriction of eta to M times I for I equal 1 and 2, okay? This symbol over here is for isomorphism, is for CR isomorphism. Okay, if psi1 is actually isomorphic to psi2, there is no match that this is very trivial. We can consider eta as just psi1 times I. And what happens is that the restriction of eta to M times 0 is going to be isomorphic to psi1, and the restriction of eta to M times 1 is also going to be isomorphic to C1, right? That since psi1 is isomorphic to psi2, then we have that here we also got an isomorphism, and the result holds true, okay? So if we have two isomorphic vector bundles, then there exists this eta satisfying actually this property. Very good. What happens with the reciprocal result? So suppose that we have that psi1 is isomorphic to the restriction of eta to M times 0, and psi2 is isomorphic to the restriction of eta, to M times 1. Okay? What happens, right, is that eta is going to be isomorphic by the previous triviality result to the restriction of eta to M times 0 times I, right? And in particular, that implies that the restriction of eta to M times 0 is isomorphic to the restriction of eta to M times 1. But this implies, obviously, that psi1 and psi2 are isomorphic. And so we get the result we were looking for. In this lecture, we walked the first steps in order to prove that every vector bundle over a contractile space is indeed trivial. Indeed, we proved a particular case of this result, that every vector bundle over an interval is trivial. In the next lecture, we are going to switch topics. We are going to consider exact sequences of vector bundles. Thank you for your attention.